All right, so well, let's get started. Just want to remind you guys again, homework night is due on Monday this time. Okay, and then on Wednesday we'll have our exams 3. Right. For classroom disinfection, I'm asking Jeffrey and Luke. Okay. So last time we start with chapter 14 by looking at the second section first. So this is on self-inductance and inductor. So basically, if you have an inductor, which is just several coils stacking together in this circuit, then in that case, um, if there's current change, then you'll have induced EMF or back EMF by the coil, okay, opposed to the change of the current, right? So if you have increasing current over here, then the induced EMF will be against the original direction of the current. If you have decreasing current, then will be along the effect of the induced EMF will be having induced current in the same direction of the current. Okay, so if your current is decreasing in that sense. All right, and so basically, if you have coil, if there's current changing, then the B field is changing. Induced B field is changing, and then in that sense, the magnetic flux of through the coil is changing. So this is called self-induction because it's the changing of the B field is due to itself, the induced B field. Okay, and we gave out the definition for induction, so it's equal to the there are two expressions you can use, either use this one or that one. You can calculate what's the inductance. Okay, has SI unit of Henry or H. For a solenoid, we went through, we used one of the equations in the previous case, so we're using delta phi over delta t. Okay, so then that gives us that the induction for a solenoid is going to be mu naught times n square. N is the turns of coils per meter, n times the area times L, the length. Okay. So if you have a solenoid, it's also called inductor in the circuit. All right, and then we also took a look on this toroid. Basically, you will be doing a similar procedure, calculating what would be the induced magnetic flux, and divide by the current. Okay, to get that expression over there. All right. Today we'll be looking at mutual inductance. That means you have two coils that are close to each other. So if there's change in current in one coil, then the magnetic field induced by this coil will be varying in the place where the second coil is placed. So in that case, you'll then have induced current in the second coil due to the magnetic field by the first coil is changing. Okay, so this effect is called mutual inductance. Okay, and to calculate the mutual inductance, you can calculate what's the flux. All right, on the second one. On the second one by the first coil induced by the first coil times the number of turns of the coil you have on the second one, and divided by the current in the first one. Okay, so we are assuming that the current is from 0 to a certain number I1. So then this is basically delta I. This is delta phi. Okay, in that case. Similarly, you can apply to the second coil the mutual inductance of the first coil by the second coil in that similar fashion. You'll be doing N1, the number of turns the coil on 1, times the flux on 1 by 2, and then divided by the current on 2. All right. You'll figure that these two will be equal to each other, M12 and M21. Okay, they will be equal to each other. So um, and in that sense, also, so this is one of the expression here. The second one you can do similarly here, like doing delta phi over delta t, okay, to get the epsilon there. So then that would be equal to, you can write this guy as m times I1 here, Okay, so it's going to be equal to that minus m, because m will be a constant number once the coils are given, and then di 1 over dt. Okay. If you are looking for epsilon 1 by 2, then it's going to be equal to minus m di2 over dt. Okay, so it's the other way around. All right. Let's take a look on the example on this one. So it says an EMF of 9.7 times 10 to the minus 3 volt is induced in a coil while the current in a nearby coil is decreasing at the rate of 2.7 amps per second. So what's the mutual inductance of the two coils? Okay. So in this case, if you call this coil to be 2, so then epsilon 2 should be equal to minus the mutual inductance. This one back here. All right. So the EMF, let's say this is on the second coil, that will be equal to minus the mutual inductance d on the first one over dt. Okay. So it kind of tell us that epsilon 2 is equal to 9.7 times 10 to the negative 3 volts. And it says the rate where the current is decreasing, so di1 over dt, that's equal to, so it says it's decreasing, so you can put a negative sign, okay? Minus 2.7 there. Then pretty much you can solve this one directly, right? This is given, this term is given. So m is equal to epsilon 2, or you can say minus epsilon 2 if you want to keep the sign there, over dt, di over dt. Okay. So minus 9.7 times 10 to the minus 3 volts divided by minus 2.7 A over second. That's going to be equal to 3.6 times 10 to the minus 3 in Henry. Okay. So Henry is for inductance. This is mutual inductance. Okay. All right. Okay. So and move on to the next section is energy in the magnetic field. Okay, so for inductor in a circuit, so basically it actually it's kind of acting like a capacitor. Okay, so it actually doesn't consume any power. I think we haven't talked about that. So I think this in the my other class I talked about it, but it doesn't consume any power, which will, yeah, I think we'll check on that later in a couple next week at some point. But let me just give this out early now. So for inductor, it's similar to a capacitor. You will not consume any power. Okay. So but however, let's take a look on here. If you have an inductor in a circuit and then there's a resistor, this circuit is powered by a battery. So then you can apply the Kirchhoff's loop rule, right? You can start from here. When you have a battery, you go from negative terminal to positive terminal, then it's epsilon naught is positive, minus IR, because you are crossing this resistor, your potential decreases. And then this is the third term is the potential on the inductor over here. Okay, so minus L di over dt equal to 0. All right, so that's the Root's rule. You're going back to this point. Now, you can multiply both sides of equations by I. So then the first term becomes epsilon times I. Second term becomes I squared over times R. The third one becomes Li di dt. Okay, and that goes to 0. The right hand side is 0, so you multiply by I is still 0. Okay, so we know that this is voltage times current. This is power, right? This is in the dimension of power. And then I squared times R is also power. This is the power on the resistor. So the third term here should also have the dimension of power, okay? So it should have that. So then this is actually the power on the inductor, okay? So this is the power delivered to the inductor. This term Li di dt. All right? So if that's power, then that's equal to the amount of energy divided by dt, right? Derivative of energy over dt, that's power. So this then equals to power, and dt and dt can cancel out. So then you can integrate this equation. So then the left-hand side will give you the energy stored in the inductor equals to the integration of the right-hand side. So if you do integration on right-hand side, now, assuming your current goes from 0 to I, so then energy stored in the inductor is going to be equal to Li di, which I is the variable here. So then it will become 1/2 Li squared. Okay. Integration of Li di becomes 1/2 Li squared, and then upper limit will be still this term, lower limit will be 0. So it tells you then energy in the inductor is equal to 1/2 Li squared. Okay, if you have current I going through it, then it's 1/2 Li squared. Okay, this is the energy. Sub M means magnetic field because inductor will store the energy in form of the magnetic field. Okay, let's take a look on the example here. This one says a 10 Henry inductor carries a current of 20 amps. How much ice at 0 degree can be melted by the energy stored in the magnetic field of the inductor? Use the value of fusion, latent heat of fusion as 334 joules per gram for ice. So the energy stored in the inductor you can calculate is 1/2 Li squared, right? Now you can use that energy to melt the ice and see how much ice can be melted at 0 degrees. I think you guys can give it a try. We can take a look on this together in a couple of minutes. All right, so I think we can take a look. So the energy store will be that, okay, and then you need the heat needed to melt the ice will be in the equation. Okay, so basically this energy will be the heat needed. Okay, so the two should be equal to each other. So you can do 1/2 L times I squared equal to m times the latent heat. Okay, so those two are different quantities. You're looking for m, how much ice can be melted. So then divide both sides by LF. So 1/2 Li divided by LF. Okay. You can calculate this is 1/2 Li squared actually times the H10, and then the current is 20 divided by this 334 joules per gram. So if this is per gram, then it will give you units of gram. So it's about 6 grams of ice can be melted, okay, using the energy stored in the inductor. All right. Questions you guys might have? Okay. All right. So next thing we will be taking a close look on magnetic field of the energy stored in the solenoid. So for a magnetic field of solenoid is given by mu naught times n times I. You can calculate this by using Ampere's law. And then we saw this earlier, but the inductance for the solenoid, okay, is going to be mu naught n square AL. Okay, I think that we saw this in the section 2. So combine those two, you can calculate what's the energy store in the solenoid, because energy store in the solenoid, it's going to be the form of the energy stored in the magnetic field. So 1/2 Li square solenoid, that's basically an inductor. Okay, that equals to L is equal to this guy, so you take that in the place of L, and then the B is equal to, or I is equal to, from here I is equal to B divided by mu naught over M. So then you can see, then this is equal to B square AL divided by 2 mu naught. So A is the cross-sectional area of the solenoid, and L is the length of it. So if you do the cross-sectional area times the length, you can see this is A times L is the volume of it. Okay. All right. Let's take a look on this one before we take a look on the density, energy density. But this one says if you have solenoid which is 1.8 meters long and has 450 turns per meter, what's the cross-sectional area of this solenoid if it stores 0.39 joules of energy when it carries a current of 12 amps? We can start with listing the knowns. So you got the energy to be 0.39 joules, and it tells you the length L is 1.8 meters. Number of turns is 400. Oh, this is small m because it's number of turns per meter. Okay, 450 per meter. And it tells you the current is 12 amps. What's A? What's the cross-sectional area A? So if you know that the energy in the solenoid, if you remember the equation from the previous slides, there's the B square times A times L divided by 2 mu, right? Now B is related to current. All right. You have N, you have I, so you can calculate B. Once you have B, this is given, length is given, so you can calculate A. Okay, mu naught is constant. All right, so let's take a look here. You're looking for A here, so you can rearrange the term. You can see A is going to be equal to 2 mu naught times capital UM divided by B squared over L, okay? And B is equal to mu naught Ni, okay? If you square it, it becomes mu naught square I N square I square times L. And 2 mu naught capital UM. There's a cancellation of mu naught and then this square, okay? Then after that, you can just put in your numbers. 2 times 0.39 joules divided by mu naught is 4 pi times 10 to the minus 7. 450 per meter squared times I 12m squared times L. It's given as 1.8 meters. Okay. So your area then is 0.012 meters squared. Okay. That's the cross-sectional area of the solenoid. All right. So the equation we had for this capital U, the energy store, is equal to this, right? And then if you divide it by volume, which means divided by A times L. So then you get rid of A times L. So then this energy density, because you do energy divided by the volume, so that gives you energy density equals to B squared divided by 2 mu naught. Okay, so and this is in the form of the magnetic field. So energy in the magnetic field, so we call magnetic energy density. Okay, so it's B squared divided by 2 times mu naught. So it's basically the field square, okay, proportional to field square, with the constant being 1 over 2 mu naught. Now, remember in the, I think not in chapter 24, that's the wrong chapter, but in the previous chapter, when we derive energy density for electric field, basically that was the energy stored in the capacitor. It has energy density of also proportional to the electric field square, right? So this is similar for the electric energy density. So these two, if you have magnetic field, then there's a magnetic energy density of proportional to B square. If you have electric field, then it's proportional to E square. Okay. In this case, the mu naught is in the denominator. This is the epsilon naught is in the numerator. Okay. All right. The next we'll be looking at RL circuit again. So in this case, if you have the a resistor that is in series with a inductor, then you close the switch again. You use Kirchhoff's rule. This is what you get: epsilon minus L di dt minus ii goes to 0. Okay. So now you can calculate, or you can do integration to get what's the current. Okay. So the current you'll be doing. I can show you guys how this is derived. Let me write down the starting equation here. So epsilon minus L di over dt minus I times R goes to 0. So we are starting from there. So you can move this term to the other side of the equation. So then epsilon minus IR equals to L di dt. Okay. Now next, what you want to do is move dt to one side, and then so move dt to the other side, and this term, so switch it over. So then dt equals to L over epsilon minus IR times di. Okay. And then you can do integration to the both sides of equation from 0 to t, from 0 to I. Okay. So on the left hand side, you will just have t, right? T equals to, on this hand side, because you have minus IR here. So this is in the denominator. So you'll give you line of epsilon minus IR. Okay. There's R here. So then you will have, now that's L. You put L down. There's R here. So when you are doing integration of it, it becomes 1 over L. Okay. And I think that's a negative sign because of negative there. So 0 to I. Okay. Now, you can move this term to the other side of the equation. So that becomes minus T times R over L. Okay. Equals to line of epsilon minus IR, right? And take this one in, and then this one in there. So minus of line of epsilon minus 0. Okay. So then this becomes line of epsilon minus IR divided by epsilon, okay, minus T R divided by L. To get rid of the exponential, you do exponential function to the left-hand side and then exponential function to the other side, okay? So e to the minus T R over L is equal to epsilon minus I R over epsilon, okay? So then this becomes 1 minus I R over epsilon, okay? And then this e to the minus T R over L. Now you can put this guy to the other side equation, this guy. Just switch the two, okay? If you switch the two, it will give you IR over epsilon equals to 1 minus e to the minus T over L R on the top, okay? Now you're looking for I, right? So then you multiply both sides by epsilon over R, multiply both sides, right? So then let's get rid of that. Okay, so this is what you get for your I as a function of T. Okay, epsilon over R 1 minus that. So which is, I think it's what you it's shown on the slides. Okay, so this is the result. Okay, epsilon over R 1 minus that. And then if you write R over L to be tau, the time constant. So this is the time constant for RL circuit. Then it's epsilon over R 1 minus e to the minus T over tau. Okay. For the voltage on this guy, so then you'll be doing that. It's minus L di over dt. So if you do di over dt, it's going to, or let's do it this derivative to this term, because then you have L here. If you do derivative of that, the first term is 0, right? It's derivative of 1. The second one will become, you'll still have this e to the minus this guy, which is e to the minus t over tau. But then you bring this down, this is R over L times epsilon over R. So that gives you, that gives you epsilon over L, but there's another L here. So then it will be just minus epsilon, okay? So you can see this is the voltage. The voltage actually it will be negative to start with. It will be negative. So if t equal to 0, it's negative for epsilon, okay? So it's very large, and then decreases down by minus with a minus sign. Okay, so that means actually increase. But yeah, just pay attention to the minus. Okay. If you plot the two for the current, it goes from 0 and saturate at epsilon over R. For the voltage across the inductor, it goes from the epsilon and then goes down to 0, exponentially go down to 0. Okay. So this is very similar to a capacitor. If this is like the discharging process of capacitor, right? That goes down, and then yeah, I guess current would be similar to the, no, current is different, right? So that's different from the what you have for capacitor. Okay. For a capacitor, your current start charging a capacitor, the current start from the maximum and then decreases down. Okay. All right. But let's take a look on this example here. It says, how much time does it take for the current in an RL circuit with R equal to 130, L equal to 68 millihenry to reach half its final value? So we're looking for current. We're looking at current and then looking for time t. Oops. You can grab the current equation from the previous slide. trouble moving this guy over. So current as a function of time t is epsilon over r, 1 minus e to the minus t r divided by L. Okay. And then you can write r divided by L as tau if you want, but not necessary. Okay. So it's asking for time t, so that it is equal to 1/2 of I final. So I final, you can refer to infinity, t equal to infinity, right? The final status. If you look at the graph, it goes like this, right? On the graph, this is epsilon over r. So that's your final value. Right, so let's take a look here. So as I mentioned from the previous graph, you can see that will be the final current. Or you can see from the equation here. So when your time is infinity, then this guy becomes 0. E to the minus infinity will be 0, right? So then final current will be epsilon over r. So that's equal to 1/2 of epsilon over r. Okay, so your I at time t is equal to that, and then what's t? That's what you're looking for. So then you're replacing ITS 1/2 epsilon over r equals to epsilon over r 1 minus e to the minus t r over L. Okay, and then you solve for your t from there. So you can see epsilon over r will cancel out. Then it's 1/2 equal to 1 minus that. So that exponential of that will be equal to 1/2, right? So then that tells you exponential of minus t RL is equal to 1/2. Okay, you're solving for t here. Then you do natural logarithm of this side and then also on this side. Okay. So it'll be minus t times r over L equals to ln of 1/2. You can write this as negative of ln 2, right? Ln of 1/2 is negative of ln 2. So then T is equal to, so this equal to that. T is equal to then L over R line of 2. Okay. So you have L, you have R, you can put in those two numbers. 68 times 10 to the minus 3, it's millihenry. R is 130 ohms times line of 2. That would be 0.363 times 10 to the minus 3 in seconds, or 0.363 milliseconds. Okay. All right. Questions you guys might have? Okay. So um so this is something similar to like the RC circuit you guys did in the lab. So if you have IO circuit, okay, so you can so close the switch S1, but keep this guy open. So then in this case, instead of charging the capacitor, you are now sending current, building current up in the inductor. Okay, so then you'll be looking at this guy because this is open, then we do not focus on that. So then current is building up on this guy. All right. After some moment later on, you'll have current equal to epsilon over R on this inductor. At that moment, you can have this switch open, but this switch closed right away. Okay, so then in that case, you'll be taking out of energy that you store in the inductor here. So then current will be withdrawn from this guy and then consumed by the resistor. So similar to an RC circuit, but this time you are withdrawing the energy from a magnetic field from the inductor here. Okay, so then you will get that. So the voltage across this guy will be decreasing down, okay? And then the current will also decrease down exponentially, okay? So this is like the discharging process, similar to the discharging process for a capacitor, okay? But we are not calling that because this is not technically a capacitor. Yeah, you couldn't charge a inductor, okay? So that's like the taking out energy from the inductor. All right. And this equation is, again, it's the Kirchhoff's loop rule. If you want to solve for the current, all right, in the loop here, then you start from there. You can rearrange the terms. You can solve for the current. It should be a exponentially decay function. Once you have that, the voltage will be L di over dt on this guy, then it will be equal to that. Okay. So the similar procedure. The current will decrease down, okay, if you plot it, and then also the voltage will decrease down as well. All right. Let's take a look on a second example on this. So this one says looking at the configuration of the circuit below here. So you have a switch here. You can see if you close the switch, then there will be current building in this inductor, right, as time goes by. And then after a while, you can open the switch, then there will be energy stored in this inductor. You can withdraw the energy, and then that can be consumed by this guy. Okay. So in this problem, it's asking what's the current in the battery through the battery, through the inductor, and then through this resistor, the 100 ohm resistor. Immediately after the switch is closed, okay, after this is closed, what's the current there, there, and through the battery. And then part B is asking you what would be the current again through those three elements after the switch is closed, long time after. So in that sense, you can set your time equal to infinity, okay? And C is asking you find the current in the battery, 100 ohms resistor and inductor again after the switch is open again. Okay, so you close the switch and then wait for a long time and then open it again. And then D is asking you what would be the current in those three elements after the switch is long opened. Okay, after it's open long time. So you guys can think about how you can solve for this one while I'm drawing the circuit on my paper here. All right, so if you just close this one, you'll see that there are two branches, right? So there's one goes this side and then one goes this side. So if you close this, the current is going to go out of the positive battery terminal, enters this junction, splits into two, right? All right. And this one and this one are in parallel with each other. So you can actually solve for this circuit first and then this one. Okay, so you can split the two. You can cover one side of the circuit. So let's focus on the inductor, the left-hand side first. Okay, so then we'll be looking for a circuit like this. You'll have a R, a L. Okay, so then the current equation for the RL circuit, we know it's IT equals to epsilon over R 1 minus exponential of minus T times R divided by L. Okay, so right after this is closed, your T is equal to 0, right? So T equal to 0 over here. So then your current would be equal to 0, right? Because e to the 0 is 1. 1 minus 1 is 0, right? So the equal to 0. So this is for the current in the inductor, right? Just immediately you turn on the switch, your current is 0, but then it starts to go up, right? Because you are building that up, okay? So this is the current on your inductor. At this moment, you can take a look now on the right-hand side of the circuit. Then you have a resistor, and there's another resistor here, and then there's this battery, okay? So on that side, the current is equal to, because they are just resistors, right? So it's just equal to epsilon divided by R, or we can call this R1, this R2. Okay, so R1, this is R2. So the first on this guy would be R1. That's R1, but didn't matter because it's equal to 0. So R1 plus R2, they are in series. Okay. So then you can calculate what's that current through this resistor. It's the 10 volts divided by 10 ohms plus 100 ohms. Okay. So that will give you 0.091 amps. So that's the current on the 100 ohm resistor. Okay, so there's 0 here, there's 0.091 amps here. So then the current going through the battery should be those two add up. Okay, current on the battery is going to be just 0.091. The two add up. B is asking you what will be the currents on those three elements long after the switch is closed. Then that means your time is equal to infinity or very large. So then the current through this guy you can calculate. So I infinity will be equal to epsilon divided by R1, 1 minus infinity to the e to the minus infinity, right? So that's epsilon divided by R1. That should be equal to 10 volts divided by 10 ohms. Okay, so 1 amps on this. Okay, on that. Now, if you look at the other side of the equation, okay, it's the same thing, right? However, now let's look at this left-hand side again. So if this is long time afterward, then the current is epsilon over R1. So current is this epsilon over R1. So that means this inductor long time afterward is basically a wire, right? It's just a wire. Because long after that, the current is not changing, so then it will not have inductance, right? You have inductance only when the current is changing. So current is not changing, so then this is just basically a straight wire. If this is a straight wire, then the current comes out of the battery will just go through the straight wire and then come back to the battery, okay? It will not flow through this branch because there's a resistor, okay? So in that case, then the current on this resistor is no longer that number, but it should be 0 because this is long time afterward. This guy now does not have reaction to the current, so they'll just go right through it. Okay. So your current on the 100 ohm is going to be 0. This is on the 2 Henry inductor. Okay. And then current on the 100 ohm is going to be 0 instead of that number, okay? Instead of that number. Current on your battery then will be just equal to 1 amps. It will be just that guy because it will not prefer to go through that, okay? So just remember in a circuit, if you have an element being parallel by a straight wire, then the current will not go through the element, okay? And that resistor. Okay. Any questions you guys have so far? So if not, then now we will have the switch open again. So now this is open. Okay, now open again. Switch is open. If switch is open now, you have 1 amps current going through this guy. Now we will not return to the battery, right? So we will go now through the outside loop here. So we'll be going through this guy here. Okay, and then just doing it that way, but it will be consumed up by this guy. Okay, so just right after it, if this is a RL circuit without this guy battery, we know that the current is equal to just exponential de decay of it minus T over R times L. Okay, so this time will be R2, okay, because that's the resistor. So when T is equal to 0, we know it's going to be still be equal to the original current. Or actually, we should just use the original current instead of that. Okay, I0, I0. Because I0 is that. Okay, if you use R2, it's not going to be the same current. Okay. So then when T is equal to 0, your I0 is equal to initial I, which is 1 amps from this. Okay, so this is still on the inductor. Now on this resistor, you will have the same current because they are in series with each other. So 1 amps. This is on the 100 ohms. On the battery, it will be 0 because this is open. So there's no current going through the battery because this is an open circuit there. Okay. For part D, it's asking you what would be the currents again after switch is open for a long time. So after a long time, you can see this T is infinity. So your I will be equal to 0. This is on the 2.0 Henry inductor. And then on your 100 ohms, that should be also 0 because it is in series with each other. And then the batteries should be also still be 0 because the switch is still open. Okay. All right. Any questions you guys have on this one? If not, I think we'll stop here today. Okay.